the improper axis of symmetry, and I have already told you, you will not understand that without the model. So today I wanted to show you the improper axis of symmetry. If you take the ethane molecule, then you can understand the improper axis of symmetry. See, this is ethane molecule. Later on, we are going to concentrate on the conformational isomerism. But now we are going to discuss only the proper and the improper axis of symmetry. Look here. This is ethane molecule. You can look like this also. This is ethane molecule. See, exactly one bond is falling on the other. This is called the eclipsed system. If the ethane molecule is like this, see, in between the bond gap, the bond of the rear carbon atom comes. So this is called staggered configuration, staggered, whereas this is eclipsed configuration. Now see here, I am assuming an axis which passes through the carbon-carbon bond. There is an axis which passes through the carbon-carbon bond like this. Look here, okay, now you can see the bond. And this is a carbon and this is a carbon. There is a bond passing through the carbon. Let me assume an axis here, and about this axis, I am rotating the molecule for an angle of 120. When I rotate the molecule for an angle of 120, I am getting an identical configuration. When I rotate again for another angle of 120, I am getting one more identical configuration. When I rotate again, the third time, I am getting the same configuration. So, in one full rotation, it assumes 3 times the identical configuration. That is why this axis is called C3 axis. So C3 axis means the axis whose minimum degree of rotation to be made to get the first identical configuration is 120. So 360 divided by 120, you are getting 3. So this is C3 axis. Now, if you take the staggered configuration, look here, now this is staggered configuration, staggered. I rotate this molecule, watch closely. I rotate this molecule for an angle of 60 degree. I rotate this molecule for an angle of 60 degree. When I rotate it for 60 degree, I am not getting the identical configuration because, watch now, look here. I don't know how far you are able to visualize this one. Look here. See, this is straight up, whereas this is slightly inclined towards me and this is inclined towards you. When I rotate this molecule for an angle of 60 degree, what happens? This becomes a straight up, whereas this becomes inclined to me and that becomes inclined to you. But the original configuration, this is supposed to be here. Is that right? This is the identical configuration. So what supposed to be actually done to get the identical configuration is this. You rotate the molecule for a particular angle and then you have to reflect the molecule about a plane which is perpendicular to the rotational axis. Now, I rotate, then I reflect the other way. Now, are you able to understand? A rotation followed by a reflection about a plane which is perpendicular to the rotational axis. If you get identical configuration, then this axis is called improper axis of symmetry. Suppose if you are not able to understand like this, I can take this model. See, I think now you can understand. Look here. There are 2 blue gray atoms and 2 blue atoms. This is CH2Cl2. CH2Cl2. C, H, H, Cl, Cl. Now take like this. I'm rotating the molecule about an axis passing here. I rotate it for 180 degree. I'm getting identical configuration because this hydrogen has come over here and this hydrogen has come over here and the chlorine here, it is here. Another 180-degree, I'm getting the same configuration. But if I rotate it for 90-degree, what happens? See, I'm rotating this for 90-degree. What happens? This is not identical because horizontally hydrogen, vertically chlorine. But when I rotate it for 90-degree, vertically hydrogen, horizontally chlorine. But if I reflect the molecule about this plane, this part will come over there, that part will come over there. Is it right? Now it is identical configuration. So if you get identical configuration nearby rotation, it is proper axis. If you get an identical configuration by rotation followed by another reflection about the perpendicular plane, then it is called improper axis of symmetry. See, this thing you will clearly understand when you are physically present in the class. On the screen, I don't know how far it can be effectively explained. Okay, anyhow, you try to understand, try to read some of the books, and then you can understand a little bit better. Okay, now we go on to the further slides in optical isomerism. So this is what we saw in the last class. So unpolarized light is having vibration in all the planes, whereas a plane polarized light has the vibration in only one plane. The polarizer is nickel prism. When a light is unpolarized light is passed through nickel prism, you are getting a plane polarized light. And when the plane polarized light is passed through a tube containing the solution of the sample, then the plane of the plane polarized light is turned either towards right or towards left. If it is turned towards right, it is called D configuration or plus configuration. If it is turned towards left, it is called L configuration or minus. This angle of turning, that is alpha, it depends upon the concentration, the light path through the solution, the temperature of the system, and the wavelength of the light used, and also the solvent used. And the specific rotation alpha D20 is equal to alpha divided by length into concentration. So from this, if you know the specific rotation, you can calculate the rotation even using this formula alpha is equal to alpha D20 into L into C. Now you see, there is another rotation called the molecular rotation. Molecular rotation M is equal to molecular weight multiplied by alpha D20 divided by 100. So I have already told you what is dextro-rotatory, what is levo-rotatory, and they are called optical isomers, and they are called enantiomers. Optical isomers are also called enantiomers. Enantiomers are non-superimposable mirror images, but identical in Grass structure. And we discussed these properties of enantiomers. They are identical physical properties and differ in optical rotation. And identical in chemical properties also. You look at this molecule. So this is butyl alcohol, secondary butyl alcohol. When the secondary butyl alcohol is treated with sulfuric acid is a dehydrating agent. So it takes off this OH. So it takes off this OH group and then this OH and H, they are removed and you are getting butene, 1-butene. Whether the OH is present here and the ethyl group is present here, you take the mirror image of this compound. Whether this compound or that compound, both are enantiomers. If you take a D enantiomer or L enantiomer, the product is going to be the same. Both will result in 1-butene. Similarly, when you react the secondary butyl alcohol with hydrogen bromide, bromination takes place in the place of OH group. The bromine replaces the OH group. Whether it is a D isomer or L isomer, both the enantiomers give the same product, that is 2-bromo-butane. When it is allowed to react with acetic acid to form ester, esterification takes place in the place where there is OH group. So the esterification also, you are not finding any difference between the products formed by the enantiomers. So D enantiomer, L enantiomer, everything gives the same product. And also the rate of the reaction is also the same. Everything is reacting at the same rate. So same product and the same rate of formation of the product. So this means that chemically we are not able to make any difference between the enantiomers. But enantiomers show the difference only in the turning of the plane polarized light either towards right or towards left. All other physical properties and chemical properties are found to be the same. But the reaction rate will be different when an optically active compound is allowed to react with another optically active reagent. Say, for example, esterification can take place when an alcohol and a carboxylic acids are mixed together. I have taken acetic acid. Acetic acid is a non-optically active compound. It doesn't have chiral center. It doesn't have asymmetric center. It is non-optically active compound. So when a non-optically active compound is acting with an optically active compound, you are getting the same product with the same rate. But I am going to combine the secondary butyl alcohol, which is a chiral compound, with another chiral compound, lactic acid. You can take either plus lactic acid and plus secondary butyl alcohol, or plus and minus lactic acid, or plus or minus and plus lactic acid, or minus and minus lactic acid. So 4 different combinations are possible. When you do like this, now the rate differs. The reaction rates are different. So such reactions where the reaction rates or mere the taking place of the reaction itself becomes a question when the combinations of the enantiomeric forms of the reactant and the enantiomeric forms of the reagent are changed. Such reactions are called stereospecific reactions. So stereo manner, they are very specific to form a particular product. So these reactions are called stereospecific reactions. Now look here. If you take a plus glucose, so glucose is also an optically active compound. If you take plus glucose and allow that to get fermented with yeast, the metabolism automatically takes place and yeast is able to ferment plus glucose. But the yeast is not able to ferment minus glucose. Minus glucose cannot be metabolized. So enantiomers normally have different biological properties. It is because the transition states, I don't know whether you know what is a transition state. The transition states, they are not enantiomeric, and different energy of activation is found for different enantiomers, which results in different rates for different enantiomers with different enantiomeric reagents. So that is the reason. I have already told you an example for this. The cetirizine, dextrocetirizine and levocetirizine. If you eat the levocetirizine, its antihistamine property is in a very smoother way it works. But dextrocetirizine, it acts much fast. So mostly levocetirizine is given. So the enantiomeric forms, they show much difference in biological properties. So the enantiomeric forms, they react with different rates with enantiomeric reagents. Now, if we have a mixture of equal parts of enantiomers, that mixture is called racemic modification or racemic mixture. This racemic mixture is optically inactive. It is due to external compensation. The racemic mixture is mentioned as plus minus or DL together. Say, for example, if I have a 15 molecules of plus lactic acid and a 50 molecules of a minus lactic acid and put together in a solution, and I pass the plane polarized light through that solution, then the 50 molecules of plus lactic acid will try to turn the plane of the plane polarized light towards right. And the other 50 molecules, which are the L enantiomers, they will try to turn the plane of a plane polarized light towards left to the same extent because they are equal in number and they are enantiomers of the same molecule. And because of these two conditions, one turning will cancel out the other turning. So the resultant light will not show any change in the plane of a plane polarized light that will come out. As such, it has passed through an optically inactive compound. So that is why the racemic mixture is optically inactive. And this is called external compensation. Why it is called external compensation? The turning of the light by one molecule is externally compensated by the turning of the same light to the same extent in the opposite direction by the other molecule. But in the case of mesotartaric acid is having two chiral centers, two asymmetric centers, whereas one center in the same molecule is turning the light towards one direction, and the other center, which is also present in the same molecule, it turns in the opposite direction. So both the turnings are getting cancelled. But here, the cancelling two asymmetric centers are in the same molecule. That is why this is called internal compensation. Normally, this racemic mixture is formed when a chiral compound is synthesized from an achiral compound. Look here, I'm taking propionic acid. See, propionic acid is not a chiral compound because it doesn't have all the four groups attached to the carbon different. Two hydrogens are there. I want to convert this into a chiral compound by brominating. When the bromine reacts with the propionic acid, the hydrogen, the alpha hydrogen is replaced. It is substituted by chlorine. Now, the substitution can take place either in this hydrogen place or in this hydrogen place. Both are equally probable. As the probability of replacing this hydrogen and this hydrogen are equal amount of bromine substituted in the hydrogen in the right hand sides and the bromine getting substituted in the place of hydrogen which is in the left hand side. Both are equally probable and you are exactly getting equal number of the 2 bromo plus isomer and 2 bromo minus isomer and hence you are getting a racemic modification. And this is a racemic mixture. Now, normally it is not at all possible to separate the racemic mixtures. If you are getting a racemic mixture and if you try to separate them into D isomer and L isomer, it is practically not possible because the physical properties are identical, the chemical properties are identical, they have the same melting point, boiling point, and solubility. So the separation is not possible. But there are some methods to separate the enantiomers into D and L forms. This separation method has a specific name called resolution. Resolution means you are separating the enantiomers into two isomers. So the racemic mixture, suppose if a racemic mixture is having one particular component in excess, it is called enantiometric excess, EE. See, this calculation is very important when you study the enantiomerism. Enantiomeric excess, EE, means where one particular compound is found slightly excess. Suppose you are having only one type of enantiomer, say plus lactic acid alone I am having. It means that it is 100% enantiometric excess because it has only one isomer. Now look here, in order to calculate the percentage of enantiomeric excess, observed specific rotation divided by specific rotation of a pure enantiomer into 100. Look here, if I had taken the pure compound, what would be its specific rotation that has to be taken in the denominator? In the numerator, what is the actual rotation observed when the mixture is taken? That is observed specific rotation divided by specific rotation of the pure enantiomer into 100. So when I do the following calculation, you will understand what enantiomeric excess is. You take a tartaric acid mixture. I am taking a tartaric acid mixture. I do not know what is the percentage of plus isomer and minus isomer present in the mixture. It is a mixture of the two isomers. So the specific rotation of this isomer is a plus 6.35 degree. But when I take tartaric acid plus form only, the pure plus tartaric acid specific rotation is plus 12.70. So I want to calculate what is the enantiomeric excess of the plus isomer in the mixture. So enantiomeric excess is equal to observed specific rotation plus 6.35 divided by the specific rotation of the pure enantiomer 12.70 into 100. So you are getting 50%. So 50% is the enantiomeric excess. It doesn't mean that the mixture is containing 50% plus tartaric acid and plus 50% minus tartaric acid. If it is so, then the optical activity will be zero. That is why you have to concentrate here. This is enantiomeric excess, which means the physical interpretation of this calculation is the 50% resultant rotation is due to originally 75% of plus isomer is present and 25% of minus isomer is present. So the 25% of minus isomer cancels out the 25% of plus isomer. So the 50% of plus isomer is excess. This is what is the actual thing. See, enantiomeric excess is 50%, but actual mixture contains 75% of plus isomer and 25% of minus isomer. That is why the resultant enantiomeric excess is 50%. So this is an important calculation. And then you can look here, configuration. There are so many types of configurations. One is called absolute configuration, which is normally found out by Givots X-ray analysis. The configuration and optical rotation, they are not related. They are not at all. They are not at all related. You take this molecule. Look here. Hydrogen, in all the three molecules, hydrogen is on the right hand side. Look here. 1, 2, 3, 4. Here is a CH2OH. Right. When I react this compound with hydrochloric acid, a chlorine substitution is taking place on the left hand side. This OH is replaced by chlorine. When the same molecule is allowed to react with the KMNO4, which is an oxidizing agent, this alcohol group is oxidized to carboxylic acid group. Look here, the changes have taken place only in this group. So, the configuration is not changed. The configuration of all the three molecules are the same. Similar configuration, no breaking of bond has taken place. So configuration is retained, but optical rotation is changed. Optical rotation depends upon what group is present here, right? So the direction and the magnitude of the optical rotation is different for all the three compounds, but their configuration is the same. You look here, in this example, you can understand. See, CH3OH, CH3OH, and here it is COOH, here it is COOH, here it is COOCH3. Only one group is changed. So both are of the same configuration. Look at their optical rotation. This is plus lactic acid. This is minus methyl lactate. Here the alpha is plus 3.82. Here the alpha is minus 8.25. See, optical rotation is not depending upon the configuration. Similarly, you look at this molecule. I've just taken the mirror images of both. CH3OH here, CH3OH here, and the COOH is alone changed into COOCH3. Now you look at these molecules, they are of the same configuration, but optical rotation is changed. So the configuration and optical rotation, they are not at all related. You cannot distinguish the molecules depending upon configuration and optical rotation simultaneously. So configuration is entirely different. Optical rotation is entirely different because the direction and the magnitude of optical rotation, it depends on the nature of the groups attached to the chiral carbon. But configuration, it depends upon the spatial arrangement. So we are going to see so many configurations: R configuration, S configuration, and D configuration, L configuration in the forthcoming classes. So with this, I